Good afternoon. Today we will look at the modeling based on Prony's method and Shank's method. Let me review the what we've seen with Paday's approximation and what is the modeling problem. So we assume we want to design a filter which, when we input the unit pulse into this filter, which has a system function h of z, and we said h of z is a rational function. It's a of z, sorry, b of z over a of z. B of z over a of z. The output is the impulse response, which in general can be infinite impulse response. And we want this output to, we'll call this x hat. We want this output to model the signal that our reference signal we are comparing, we want to model is x of n. So we take the difference between x of n and x hat, and we call that e prime n. This is the error between the modeling generated by the filter and our given signal x that we want to model. Now we generally will look at minimizing an error. This error, we call this ES, and that error is going to be the least square ES is the sum from n from 0 to infinity of the absolute value of e prime n square. So this is the mean square error of between the output and the given signal. So the target is to minimize this error by choosing the best possible filter. So this is in general. In Paday approximation method, we have chosen a different approach. We didn't minimize all this. This would be a general goal. We took a minimal approach, which in Padday approximation, we just force this error to be equal to 0. So absolutely no error for n from 0 to p plus q plus 1. Remember, you have q degree is q, degree of b of z is q, degree of p of a of z is p. So this is q, and p is the number of poles and q is the number of zeros of the filter. So in Padday's approximation, we can make sure there is no error for the first p plus q plus 1 terms, and then after that we cannot say anything. So it doesn't allow any prediction. It just it's a representation of the signal x with the x hat, and it matches perfectly for a finite number of samples. So today we are going to look at this problem here. So instead of having a perfectly no error, and then don't care about what happens for n greater than p plus q plus 1, we will minimize this. We try to minimize this quantity ES. Okay, so we'll see it's the full ES. We'll get there by stages, and we have different approaches. So the first one that we're going to look at is Prony's method. So in Prony's method, what we will try to minimize, So we still design a filter h of z, and that is, the setting is the same, but we're gonna try and minimize an alternative error. So the idea is to take this error here, the E prime n, and look at a different error, which we will consider a filtered version of that error. So instead of looking at En, we take E prime n as error. We will take that error and we filter it with a filter which is an A of Z. We will see that one. So that we produce a filtered error signal, which is called En. And now our objective is to design the H of Z such that we minimize this filtered error, but for n from q plus 1 to infinity. So we will make sure that the error, we'll try to keep the error small for all the samples after q plus 1. Remember, q is the number of zeros in the H of Z. So that is a different goal. I mean, slightly different error, but you can imagine that if you make this one small, then also this E prime will be also small, which is the original goal we had here. So let's redraw this problem in including this filtered error. So we call this filtered error signal. So let me draw it in a new page. So we will have filter H of Z here, which produces our H of N, which is the X hat N. But instead we can filter it. So we would have this compare with this, with the minus, and we get the E prime N. So we can redraw this and then pass this into the filter, which is the A of Z, to produce En. So we're going to redraw this as, okay, the first part is the same, H of Z. We have the Hn x hat n. Now this block here, you see, it's applied to the difference between this and this. So we can move this block here and here due to the linearity. So we can put an A of Z here, followed by this term. So we get, and then we put another A of Z here. And so that means we filter both the given signal Xn and we filter also the X hat N because we're applying superposition. So you can see that this gives still En in the same way as the previous diagram. And let's see what you find here. Remember, H of Z was B of Z over A of Z. So what we did artificially is to get rid of the denominator in this side. So if you look at the whole block you have here, this is the cascade of BZ over AZ times AZ, which is equal simply to the BZ. Which means that in terms of the sequences, if this was delta N coming in, the output of this is just an FIR filter. Okay, with a Q taps. So you get a sequence. The impulse response of an FIR filter is simply the sequence Bn of the taps in the filter. So you actually here you have exactly Bn. Now here we have the given signal, and the output signal is going to be the convolution. So what we have here is the convolution of An, that's the sequence of the denominator, with the input signal Xn. So we'll call this the B hat n. So that this error is exactly the difference between B n and B hat n. Okay. So in there is something to note that Bn is a finite sequence of coefficients going from 0 to q. So we have only q plus 1 non-zero terms in this sequence. While here, we assume to have an infinite signal coming in, which it gets convolved with this another FIR filter, which is only AZ, which then results in an infinite length sequence B hat. So we don't care what happens for n from 0 to q, but what we care is to minimize what happens between after q, so from q plus 1 to infinity, because that's where this term will be different from 0, because this one will be 0 after q. From q plus 1, Bn is equal 0 for q plus 1 dot 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 for n greater or equal than q plus 1. So this term will be 0, and then it will be compared with whatever comes out of the B hat. Okay, so now remember, we are free to design both B of Z and A of Z in this scheme. So let's write all this in terms of the Z transform. So first of all, E prime of Z, so this one, is equal to X of Z minus H of Z. And then, as we know, it's just X of Z minus BZ divided by AZ. So if we multiply both sides by AZ of this equality, so this was A prime Z, we end up saying A of Z times E prime Z equals AZ times X of Z minus BZ, which is exactly our EZ without the prime. Okay. So this equation is what is represented in this diagram, in the second diagram up here. So let's write it in the time domain. So we can write it here in the time domain. We can say this EZ in the time domain is En, and that will be equal, let's write this term here, will be equal to An convolved with Xn, which is what we have called B prime n, minus Bn. Now, the Bn, we said, is 0. This term is equal to 0 for n greater than q. So if we look at the set of equations that we have in here, you can see that for the unknowns are ANs and the BNs, right? These are both unknowns. But if we restrict ourselves to n greater than q, then this term is 0. And we only have equations in the unknown an. So let's write that in terms of the sequence an. So how many unknowns an? The sequence an is going to be 1, a1, a2, up to ap, which are the coefficients. These are the coefficients of a of z, the polynomial a of z, which has degree p and hence p plus 1 coefficients. So the idea is that we can find the AKs to minimize this error, at least for q greater than for n greater than q. So we will look at this error. We'll call it a p comma q because it depends on both p and q. So this error will look at only the error from q plus 1 to infinity of this en, this filtered error. And because that's the easy part where we have decoupled the unknowns. We only have to deal with the sequence an of unknowns, and the bn we don't need to care about them. We can find those later. Once we found the AKs, we can plug them in and find the BKs. Okay, so let's see how to minimize this quantity. Okay, well, we can write what is En. Okay, En is so let's write this. So we have this the infinite number of error terms from q plus 1 to infinity, and En we said it's just the term AK. So this is the convolution of AK with xk. So an with xn. So we can write the convolution of a with x as we had before. We've seen it here. This convolution here, convolution an with xn. We'll write it explicitly here as a sum from k from 1 to p of ak with x of n minus k. And since the first term of the sequence an is a 1, I isolate that so I can have plus xn. That's the first term, and this has to be squared. So all this inside here was our en, the error that we. So let's minimize over this sequence of AKs, okay? Because this one was known. So the only remaining unknowns are the P unknowns to find AKs of this, what we've called the PQ error. So we want to minimize this this quantity. You see, it's a norm of a vector. So, and it's operation we've already seen a few times. So it means we need to take derivative, partial derivatives of this objective function with respect to the AKs. So that means we're going to take partial derivative of E of this error term, objective function EPQ, with respect to all the AKs, and set that equal to 0 for k from 1 to p. So this will give us a set of equations to solve and find where the minimum will be. So the next step is to say this take these derivatives with respect. In fact, we actually take them with respect to AK star. Just it's the trick we use when we are dealing with complex variables. So the AK, we take derivative with respect to AK star, and set that to 0, which is equivalent to writing that as the derivative of the sum of E. Remember, this is En, all this is En square, right? So we write En absolute value square as En times E star of N. Okay, so this is what we are, and then it was from N from Q plus 1 to infinity. And we derive that with respect to A star of K. So you can see one thing, that in where is A star? A star only appears in En star. So this term will be a constant when you derive with respect to that. So this is equal to, and the sum of the derivative of the sum is the sum of derivative. So we can rewrite that as a sum from Q plus 1 to infinity of En times the derivative of E conjugate of N with respect to A star of K. And that we set equal to 0. Okay. So what remains with E star N? Remember, E star N, let's write it here, is just the star of version of that. So it's going to be A star K times X star N minus K plus X star N. Okay. So this is K from 1 to P. So when you take the derivative of E star N with respect to A star K, you see this is a sum of many terms, but there is only one term which contains A star K. So, and that term multiplies this number. So this term here, let's do it this way. So this derivative here is just this quantity here, because the rest is not depending on the A star K. So what remains is that this is equal to the sum of the En times X star of N minus K. Okay, now this is telling us that the scalar product of the sequence En with the sequence X star of N minus K is 0. Okay, of this sequence. So this is an orthogonality condition. Principle. So this principle tells us that the error should be orthogonal to the signal X star N minus K shifted. And this should be true for all K from 1 to P. So we have built P equations involving the unknown AKs, because now the AKs are still hiding in here in this error term. So let's write that. So that orthogonality condition, we're going to write it sum from Q plus 1 infinity. Now the En, we rewrite it as Xn plus the sum of the AKs, that's where the unknowns are, of Xn minus K. This is from 1 to P. Sorry, let me use for this internal, let's use, okay. The reason for that is that, so let's use, since K is the index that we use for the derivative. Let's leave that k for outside sum. And then here we had x star n minus k. So we have to do this sum over L, and that's just the convolution of x with the sequence A. And it tells us all the variables Al from 1 to p are in this equation, and this is set equal to 0. So we can rewrite this one by reshuffling things. So this is like a system of equations for k from 1 to p. And the unknowns are here. These are the unknowns. And I have p unknowns in each equation. And I'm going to rewrite this in a different order. Now, what I can do is take this, put it on the other side, and swap this sum, inner sum over L, with this sum over N. So we will rewrite this as a sum for L from 1 to P of the AL multiplied the sum. Now the sum over N is going to stay in here. So I have sum over N of the x n minus L in here times the x star of n minus k. Now I have one term left, this one here, that you see this term here multiplies this term here. So and there's a sum over n. So I'm going to put that on the other side of equality, and so I will have minus a sum from n q plus 1 to infinity of xn times x star of n minus k. So again, this is my I have rewritten the set of equations, and you can see that this is kind of a coefficient multiplying the unknown variable AL. And this coefficient, if we look into it, we can actually see it looks like an autocorrelation. Now, the X sequence is a deterministic signal that we know, and what we are saying here is this is it looks like an autocorrelation, and simply we are assuming these signals start at q plus 1. So we will call this the Rx of k and L. And it's deterministic. It's not, these are deterministic signals. So it's not the autocorrelation function we have used for random processes. So we call this the deterministic autocorrelation. Now we can also recognize in here that this is actually the autocorrelation, this the same deterministic between k, so the Rx of k comma 0, because we have n minus L is actually n minus 0. So this side is Rx of k. So we can actually write the normal, these are the normal equations, and we'll call these the Prony normal equations as a sum for L from 1 to P of AL times Rx of k comma L equal to minus Rx of k comma 0. Now, as you can see, if you are given all the samples of x, with all those samples, you can compute the Rx of KL, and then for any K and any L, so you will have these are known and these are known. And all this gives me a linear system of equations for K from 1 to P in the unknown AL. So I can find the AL. So linear system, as usual, we will write them in a matrix form. So what's the matrix form for this? Well, let's see. When L is 1 and K is 1, you will have Rx 1, 1. Then you have Rx 1, 2. And so on until Rx 1, P. In the first line, multiplying a vector with A1 to AP. Right? If you see the first row of this matrix, multiply this column of unknowns, you have exactly the first equation where you have set K equal to 1. And you can go on until you hit K equal to P. So you will have Rx of P comma 1, Rx of P comma 2, until Rx of P comma P. So this is this deterministic autocorrelation function put into the matrix form. On this side, you will just have a vector which is minus Rx of 1, 0 down to Rx of P comma 0. So we have all these vectors available. This matrix, we can actually write it we can rewrite this in a compact form as the R matrix Rx, which is the deterministic autocorrelation matrix, times the vector, let's call it AP to remember that it has P variables, equal to minus vector R X, and this vector is the vector starting from Rx of 1, 0, and ending with Rx of P0. So what we know about this matrix? Well, first of all, this matrix is Hermitian matrix. And obviously it depends on the signal we want to model. So this Hermitian matrix can be also computed as a product of two semi-infinite matrices, and we will show you how it looks like. You can write this as the product of a matrix XQ Hermitian times XQ. And also you can write the vector Rx as X Hermitian, so XQ Hermitian times XQ plus 1. So why is that? So what does the X matrix look like? So this XQ matrix, you can actually verify that the XQ matrix is the matrix that you build by taking the samples of X from Q, X of Q plus 1, and so on to infinity. So we're going to put them in the first column. And then starting with X of Q minus 1, X of Q, X of Q plus 1 in the second column, and so on until you reach X of Q plus 1 minus P. Okay. So you kind of go back until you get, and then you go on until here you will have xq, and you keep going. So these are semi-infinite. This is a semi-infinite matrix. It goes on. The number of rows is infinite, but the number of columns is fixed. And if you look what that looks like in terms of this matrix, let's make a picture. What is X Hermitian? Well, it's the transpose of this. So you will have to picture this. You will have a very like a infinitely fat matrix, Hermitian, times this infinitely tall matrix xq. So this is xq Hermitian times xq. Why is that infinite? Because it corresponds to the definition of the sum. So the entries of the matrix Rxkl are this infinite sum, which are the product of xn minus l with x star n minus k. So if you look at that, in terms of this, the first row is this column, and the first column, you can see what is this doing is taking the product of the first row terms conjugate because of this Hermitian, and multiplying them by the corresponding columns of xq. So you have all the possible values of Rx of k comma l, which are the sum from n from q plus 1 to infinity of the x n minus l times x star n minus k. So in this way, we can write this as we can think of this as the result of this infinite product. Okay, we'll see why this is an interesting way of seeing at it. But let's do one more step. So you can, why is the Rx vector also given by this infinite matrix times the vector xq? So the vector, this vector xq is simply, so this we have the infinite matrix times the infinite vector xq, which is just 1 xq plus 1, which is just this term here. So the vector starting at q plus 1 with the samples from q plus 1 to infinity. And that's because if you remember, we are looking only at Rx. What the vector Rx was actually starting with R 1, 0, R 2, 0, and so on until R P, sorry, R X X X of P comma 0. And that was, and this R1 is obviously the same as here, where the L is 0. So when you place L0, you will have, you're starting from Q plus 1. So you will have this vector starting from Q plus 1 and then multiplying the corresponding X matrix, which has the remaining terms of this product and sum. So this means that we can rewrite this system of the original system of equation, which have the Prony normal equations, and in terms of this replacing this notation into something like X Hermitian Q times X Q, that is Rx, times the AP vector unknowns, is equal to the X Hermitian times the vector XQ plus 1. So how do we solve this this system of equation? We can, well, we know we can solve this one because this is square matrix, and if its determinant is non-zero, we can definitely solve this and find AP directly. But we can also see what that means if we look at it from this point of view. This means we are you can imagine the XQ Hermitian is not there, and what you are saying is that XQ times AP is equal to minus XQ plus 1 vector. Now, what does this represent? This represents a convolution of AP of the sequence X with AP, okay? And we want that to be equal to this vector XQ plus 1. Now, if you see, this produces infinite number of equations. You have infinite, let me go here, infinite number of equations. And we know this cannot be solved as a system of linear equations. But we know what we do when we have too many equations. We go for the least square solution. And the least square solution, of this system of equation, how do we find it? Well, we exactly do multiply both sides by XQ Hermitian. So if you multiply by XQ Hermitian both sides, then you get the previous equation, the Rx equal AP, which is solvable. So what you are looking at, the least square will give you a solution for which the XQ times AP is approximately equal to minus XQ plus 1. And it minimizes the square error from this side to this side. So the Prony step 1 will find exactly this this solution. Okay. So we can in practice we can do directly solve the first this system here given X, or we could use this one, have obviously many equations, a large number of these equations, and then find the least square solution. So MATLAB will directly deal with that, which is, so it's equivalent to finding least square solution of this without pre-computing all the autocorrelation values. So in a way, it's more efficient to solve it this way if you think about it, because you don't compute in advance all the autocorrelation, deterministic autocorrelation samples that you need. Okay, so we have not finished, because once we found the APs, the vector AP, so we find all the vector AP with the P unknowns. So we have just solved the denominator, but let's check first of all, what is the error? What that error, EPQ error, as a function of this AP, let's call it optimal. Okay, the best value, which minimizes the error. So let's see what is the value of this error when it's minimum. So in order to do that, we just need to substitute the AP that we have found into the error expression. So we're gonna write the error expression. We know it's just from the definition is the mean square, sorry, is the least square error. We write that as En times En star. And let's just expand, let's replace the star, okay? So we're gonna say this is a sum from q plus 1 to infinity of En times, well, Xn, the En star was Xn, we can put the star inside, plus, we said the sum for L from 1 to P of the AL times, so this was star times X n minus L, also star. So if we move inside this sum onto both terms, we will have this equal to sum q plus 1 to infinity of the En times the X star of n. So this is the first term. And the second term, we're just going to swap the order of the sums and have the sum from L from 1 to P times the AL star times the sum of the En times the X star of n minus L. And this is for q plus 1 to infinity. Okay, now what did we see before? That when do you have the A optimal? You have A optimal when the orthogonality conditions are satisfied. That is when the gradient is 0. When are those satisfied? Well, the orthogonality condition told us that these quantities are always 0 for any L. So for any L between 1 and P, these were the orthogonality conditions which are satisfied by the A optimal. So satisfied by the A optimal solution. And A is hiding in here, right? The AKs are also in here. So anyway, these go to 0. That means all this term disappears, and the only surviving term is the first one, this one here. So let's expand it now because we know this is gone. Now we can replace En with its actual expression, which is just Xn plus the sum for L from 1 to P of the AL times X of n minus L. And all this multiplies the X star of n. And this is from q plus 1 to infinity. So the corresponding, so then we can expand that. Now we have here, the first term is sum from q plus 1 to infinity of Xn times Xn star, which is simply Xn absolute value square. And then we have plus, let's take the sum over L out. And then we have the ALs times the sum from q plus 1 to infinity of the Xn minus L times X star n. And we've seen this, what this is corresponding to. This is actually the Rx of 0, L. So this is the expression of the error, the residual. Once we found the AL, we can plug the AL in here, and we know the Rx at 0L samples, and we know the total energy of our signal from Q plus 1 to infinity. So this is known. These coefficients are known. We derive the AP opt to replace in here. So we have the value of this minimum, okay, of this error now, which we've minimized. Now, last step we need to do is to find the numerator of our filter. Remember that the filter was H of Z equal B of Z over A of Z. So what we did up to now was just to find a set of equations which could give us the denominator, irrespective of the numerator, because we use the values for n from Q plus 1 to infinity, where the numerator doesn't matter. Okay, so there's one little step to finish, is to find the BKs such that the error En is equal to 0 for n from 0 to Q. And remember that we wrote the set of equations was En is equal to the convolution of An with Xn minus Bn. Now, this is a set of equations in the unknowns Bn. So we can always write the this and find the corresponding Bn. Okay. So Bn equals the Xn plus, so we want this to be 0, En, we want this equal to 0, right? So then it's just Bn equals to the convolution of An with Xn, and the An starts from 1, and then it has A1, A2 to AP. So you have sum for L from 1 to P of the ALs times X of N minus L. So these are the coefficients. I have all the coefficients ready, and I can find my filter designed by Prony's method, which did the following thing: made the least square error of the model with the reference signal as small as possible from Q plus 1 to infinity, and made 0 error from 0 to Q. So this filter is called the Prony filter, and gives this model, which allows for prediction into the future. Okay, so this was the first method we looked at today. I think the next thing we will see is the Shanks method. So let's start a new page and see what the Shanks method offers differently from Prony. Okay, so the Shank method, we go actually back to the original error. Remember, Prony's method was playing a trick of minimizing the error after the filtered error. So an error after it's filtered. Now, instead, in Shanks method, we actually go back to the original error E prime, which is just directly the error between the model and the output of the filter. So the trick is to think of H of Z of our filter, which we said is B of Z over A of Z, we will think of this as the cascade of two filters. One is a filter 1 over AZ, and then which is an all-pole filter, and then followed by an FIR filter. So let me draw this. We will, as usual, send the unit pulse at the input. We'll have the first filter, which has a system function 1 over AZ. Now this is an IIR filter, and it's called all pole. There's no zero filter. We'll call the output of this, the impulse, the infinite impulse response output of this, GN. And we said the following: this GN will be further filtered by an FIR filter, okay, with system function BZ, which is just a polynomial, and the result is our X hat of N, our model. We know we compare this with our XN, taking the difference, and the result is our E prime N, which is the direct error that we are looking at. So the idea is to do the following operation. So the target, okay, the target is to minimize over all possible filters H of Z, the quantity sum, this time from 0 to infinity, of E prime N. So we are now looking at minimizing the error over from 0 to infinity. Remember, we are giving a signal Xn from 0 to infinity, all its samples, and we want to have a filter which reproduces or models this this signal in the best possible way, in the sense it minimizes this across the entire range from 0 to infinity. In Prony, remember here we started from Q plus 1 to infinity. And then we from 0 to Q, we said no error. So in a way, Prony's method is a bit greedy on the first Q plus 1 terms, because it allows no error in the first Q plus 1 and then minimizes the residual. Shank's method is more fair, in the sense that it allows error to be spread all from 0 to across the entire range of N, from 0 to infinity, and tries to minimize it all. So then this is called direct method, because it operates on the entire Xn, and it looks directly on the error E prime, not as Prony on this alternative error. Okay, to get there, it's requires some work around to be able to get to this representation. Okay, so this is our error. The target is to minimize that. Let's take it in steps. Okay, so the idea is, first of all, let's describe what is the output. What is GN when you have an all-pole filter? That's the all-pole filter has an impulse response which is equal to delta N minus plus the sum from K from 1 to P of AKs times G of N minus K. How do we find this? This is simply the recursive difference equation, which gives you the output Gn as a function of the previous outputs. You can see if you do the convolution of Gn with the input, you will see that you get infinite output because this is recursive. So we know how to write these recursive equations starting from the Z domain. We just have to do inverse Z transform, and you will find the corresponding difference equations that govern the input. They give you the output recursively. Okay, so the step one is to see, you can see that what is this E prime n? Okay, let's see what it is. We're going to write it as a function of this Gn. So we know it's xn minus x hat of n. But what is x hat of n? So this is xn minus how do you get x hat of n? You take Gn and convolve it with the Bz. So we're going to do Gn, which is infinite duration, convolved with the sequence Bn, which is the FIR filter. Okay. So we are going to look at it in this way, and we can find the A case using Prony's method, and then the B case to minimize our objective function here. Okay, so let's do this in terms. Let's do this minimization. Okay, as to find the B case first. So let's start it here. I'll just change color. Okay. So the plan is to find the BKs that minimize this objective function. We'll call this ES. Okay. ES. Okay. So, and we use the fact that the Bn are involved in this equation. So we can find this for the B. We can use these equations E prime in the ES and find the Bn that minimize that quantity. So the result will be a function of the G function of the Gn infinite impulse response of the first part here. So let's write this in terms of this Gn. Okay, so the idea is to start from to find the Gn, you need to find this first filter AZ. So before finding the BK, you first find So the plan is to work in this way, where here now we have Gn, which is infinite sequence that we don't know yet, but we will know it once we know the AKs. So first find the AKs. And how do we find the AKs? Well, we use Prony's method. So remember that Prony, we studied Prony's method where with the P and Q, right? Now that was when we had BZ over AZ. But here we have Q is equal to 0. So it's much simpler because, and what does Prony do? When Q is equal to 0, it means we don't have to find the BKs. Okay? We just have to find the AKs, and we find these AK that minimize the sum. Remember, it was from Q plus 1. So this is going to be a sum from 1 to infinity of the E prime N sequence square. So we first find the AKs this way, just directly using the Prony's method. That will give me the AKs. Once we have the AKs, we can obviously compute the Gn because it's dependent on these AKs. And then once we have the Gn, we can find the Bn, as we will do now. So we find find BKs to minimize this ES. So we proceed. Remember, ES is using E prime. ES was the sum. This ES is the sum from 0 to infinity and from 0 to infinity of E prime N square. So we take the usual derivative of ES with respect to the conjugate of the BKs. And we use the same trick as before. We said it's a sum from 0 to infinity of E prime N, the partial derivative of E prime conjugate of N with respect to the B conjugate of K. So we have to set this equal to 0. So if we remember what was AEN, E prime N, we can write it as XN minus BN convolved with GN, which we can write explicitly as XN minus a sum from L from 0 to Q, because we have Bn has got Q terms, Q plus 1 terms from 0 to Q of the BL times Gn minus L. Now, Gn minus L is obviously infinite, so you will always have for n can go to infinity. By substituting this into here in the same process as we did before, we just, instead of having in Prony, we had the sums from Q plus 1 to infinity. Here, the sums will be from 0 to infinity, but the result will look the same. We will end up in this orthogonality. We'll find that the orthogonality condition will give us a sum from 0 to infinity of the E prime N with the G star of N minus K. That is equal to 0. So all these we have for K from 0 to Q. So we have Q plus 1 equations in the unknowns bk, which are hidden in here, okay, because E prime has the bk's inside, as you see it here. So when we substitute E prime and we rewrite it exactly as we did before, but we will get sum from L from 0 to Q of the BL times the sum from 0 to infinity of the G n minus L times G star of n minus K. So, which is the deterministic autocorrelation function of the sequence G. So we'll call this term here the RG of K comma L. And that's equal to the sum of xn, so the sum from 0 to infinity of xn times G star of n minus K. So these the orthogonality conditions give us these equations, and you can recognize here, this is the Rxg. So the deterministic cross correlation between the sequence xn, deterministic signal, and the impulse response G and K. So we find this is function of K alone. Now, this is the general setting, but we will note one thing. First of all, we can show property 1 is that this deterministic autocorrelation function is actually dependent not on the pair KL, but is dependent on the difference of K minus L. So RG of K minus L. The second property is that the RG of K minus L is equal to RG conjugate of L minus K. So that's the Hermitian property. So you see, although they are deterministic autocorrelation functions, they behave like autocorrelation functions. And these are quite simple things to verify just by substituting and finding the result. So I'll just show you maybe the first proof, the proof of proposition 1. Let's go. Of property 1. Okay, so how do we prove that the difference that RG of KL, K comma L is actually an RG of K minus L? So we actually look at RG of K plus 1 comma L plus 1, and we check, is this equal to RG of K comma L? Why? Because we kind of shifted both K and L by 1. So we shifted them by 1, but the distance K minus L is the same. So we want to verify this equality. If that is true, then we can say, if it's true by shifting by 1, it will be true by shifting by any amount, both by the same amount, both. So the result is K minus L. Okay, so let's compute this quantity. So this quantity is, from its definition, we had the sum from 0 to infinity of G, we have Gn minus L. So, but that minus L will be L plus 1, because we have L plus 1 here, times G star of n minus k, and now it's an n minus k plus 1. Okay. So what's the trick is to change the summation, start summation from basically replace n prime, do a change of variable in the summation, n prime equal n minus 1, and same n minus 1. So if we do a change of variable, we will end up having a sum for n prime going from minus 1 to infinity of Gn minus this n prime minus L, G star of n prime minus k. So this quantity is going to be equal to, we're starting from minus 1, okay? So we can write it as a sum from n prime from 0 to infinity of the same thing, n prime minus L, G star of n prime minus k. And then we add the missing term, which was minus 1. So this is plus G of minus 1 minus L times G star of minus 1 minus k. Okay, but remember that Gn is causal, which means that Gn is equal to 0 for n less than 0. And you can see here that the indices in here are always less than 0. So this term is never there. So once we use this property, then we can rewrite the orthogonality condition in here as the sum of bk rg of k minus L equal to rg, so rxg of k. And these, so this is for L from 0 to Q, and we have K equals 0 to Q. So total, we have Q plus 1 unknown and Q plus 1 equations. So we can solve them, and we can write it as in the matrix form, still write it in the matrix form as RG matrix. So what is the RG matrix? Is the autocorrelation, deterministic autocorrelation matrix, where we replace where the entries are RG of K minus L times the vector B. The vector B is with Q terms, and that is equal to the vector RXG, which we have. So this is a Q plus 1 times Q plus 1 system of equations. We solve it for BQ. So the key thing is we need to have computed the RJ. So the RG, and the RG, we will get that one from having solved for the AKs using Prony's method. So we still need to compute the corresponding minimum. So what is the ES of this this B opt, A opt? So this was the BQ vector, and then we had an AP opt, which we found from applying Prony. So we can write that as equal again, the sum from 0 to infinity of the E prime n square. We do the same trick as before, replacing the expression for the error. So we'll have E prime n times x n, the E prime conjugate. So we will have a conjugate here times a sequence from, we had the xn minus the convolution of b with g. So that convolution, we write it as a bk, and the sum for k from 0 to q of the bk with the g star of n minus k. And star is there too. So if we spread the outer sum inside, you will find that you get the E prime. You have the sum. Let's do it here. We'll have the E prime n times x conjugate of n from 0 to infinity minus the sum from, we do first the k from 0 to q of the b star k's times the sum of the E prime n times g star of n minus k. This is from 0 to infinity. But we recognize that these are the orthogonality conditions, which means these are 0 whenever you have the optimal, you found the optimal vector b. And so the only thing remaining is this term, and we can expand this term as xn minus bk g n minus k conjugate. No, not conjugate. This is the sum from 0 to q. This is the sum from 0 to infinity. This times the x star n. So the result of this is a sum of xn square, absolute value square, which is the total energy of the signal x, minus the sum k from 0 to q of the bk's times n from 0 to infinity of the g n minus k times x star of n. Now you can see that this is the, you can read this as the deterministic cross correlation of g and x for minus k, because we have this minus k. And then that is equal to our gx conjugate of k. So we can write it in more compactly. This error, this ES, is equal to Rx of 0, because this is, remember, Rx of 0 is the energy of x, minus the sum of q plus 1 terms, which are the bk's, times this cross correlation xg star of k. So these are terms that can be give us the residual error, which we have minimized, the minimum value of this residual error. As before, we can write this matrix in terms of this problem in matrix form. We've written it in terms of the matrix RG, but if we look at it in terms of a system of infinitely many equations with just the unknowns BQ, then we can write it also as a least square solution. So let's see how to write this. We will say, we remember what the problem we are solving is. We have an input Gn into the filter Bz, and the output is our Xn. So what is what is the problem we are really solving in this case? We are trying to find the filter Bz, which minimizes the error between the filtered the filter Gn, which is this Xn, and the actual so this is the hat, and the actual Xn. So we're going to compare that with our Xn. So this is what this the problem boils down. What we are solving, we are trying to find this filter, FIR filter, such that when Gn is input, which is not just an impulse, we have this Gn input, this filter, we get X hat, and we want to make that error E prime to be minimized. Okay, so we can write this as the convolution of Gn. So this is the convolution of Bn and convolution Gn. So how do we write convolutions? Well, we can write it as the matrix G0. Now Gn, it starts from 0, and it's 0 before. So it's G0, G1, G2, and to infinity. Then the next one starts from 0. Then you have G0, G1, G2, and go to infinity. 0, 0, G0, and so on. And as much how many columns you make as many columns you need for the unknown vector, which is B0 to BQ. So in total, we will have Q plus 1 columns for this matrix, which we will call this matrix G0 matrix. This vector, we'll call it BQ vector. And what is the output have to be? Well, the output we want, this is the convolution of Gn with Bn on this side. On the other side, we want it to be equal to Xn. In fact, we want it to be every sample at the output, we want it to be equal to X0, then X1, and then to infinity. This is the target, right? So we have many equations involving the unknowns B, the B's, and we know that they have to match. That we want this to be true. Now we cannot. We have too many equations and more equations than unknown. So we go look at the least square solution. So what does the least square solution? It minimizes the norm of this vector G0 BQ minus, let's call this vector X0 square, which is the mean square error between, tries to minimize this this quantity. Okay, they have to fit as much as possible to minimize get the least square error. So how do we solve this system of equation G0 BQ equal this vector X0? Well, we've seen how to solve this by multiplying by G0 conjugate on both sides. Sorry, G0 Hermitian conjugate. So we get the G0H times G0. And if you see the G0, this is a semi-infinite fat matrix times the semi-infinite tall matrix. The result is a small square matrix Q plus 1 by Q plus 1 times the vector X, the vector BQ, which is Q plus 1 terms, so BQ plus 1 terms, and that will be equal to G0H times, so this is going to be a semi-infinite fat matrix times the semi-infinite X0 vector. The result of this is a vector of length Q plus 1, and we know that that vector is exactly the cross correlation between G and X. Okay, so that's the equivalent view of this. So if you write when you write the solution of this least square problem, it tells us that BQ vector is equal to GH times G0 all to the minus 1 times G0 H times the vector X0. So the corresponding solution, we can find it as a least square solution of this. So tomorrow we will see how this Prony, this model becomes the Prony method becomes very simple with all poles. So let's say we find the how to do the first step, the finding the all pole model with Prony, and then we will have a look at some other problems where modeling is equivalent to finding, looking at finite block length cases. So I'll stop here for today, and see you tomorrow.